Okay, geometry, we have an interesting section here in 10.8 called geometric probability. And the key to this section right here is realizing that we're using all the stuff we've been learning about area in chapter 10 to talk about something that's completely different here. And the concept at play here is probability. Now, probability is one of those things that used to only get discussed a little bit later on within math. But now there's been an emphasis over the last, I don't know, 10 years or so to try to bring probability into all the different levels of math that you guys learn. Now, for those of you guys who might very well take statistics your senior year after you finish Algebra 2 next year, which is a really common route that a lot of seniors are going these days who are on your path, everybody, probability is one of the major topics within statistics that you guys will talk about. But it tends to show up a lot on standardized tests, which, we might take again in the future. So let's see how all this works. All right, so we're going to start off talking about the concept of probability and trying to define the word here. And the definition of probability is the likelihood that an event might occur. So when you look outside on a day like today and you see a relatively overcast skies and a lot of clouds and some wind, you think there's a decent probability that it might rain today. But if the temperature's up as high as it is, there's probably not a very good probability that it's going to snow. So when we talk about probability, we just mean whether something is likely to occur or not. And a lot of the games that I know my family's been playing as we're sitting here stuck at home kind of bored deal with the concept of probability as well. Things like Yahtzee, things like poker, blackjack, Monopoly, a lot of games like this are all based on the concepts of probability. So the simple definition of probability, and this works for all kinds of probability here, is basically this little formula, which doesn't look like much of a formula right here. It's just a quotient. And when you're talking about an experiment, we always take the number of successful outcomes and we divide that by the total number of outcomes that could possibly occur. And that's it, guys. So the simple formula for probability is successful outcomes divided by total outcomes. And this concept right here becomes pretty important, guys. The P in the middle here stands for probability. And the way to read this mathematically, I know it can look like a foreign language, is that 0 is less than or equal to your probability, which has to be less than or equal to 1. What is important to understand about that concept is that the lowest that a probability can ever be is 0. There's no such thing as a negative probability. If something is impossible, we say that it has a probability of 0. And the other way to read this right end right here, is that the highest that probability can ever be is 1. So if something is a guaranteed outcome, a 100% chance of it happening, we say that the probability is 1. But in almost every other case, probability is going to be a number in between 0 and 1. So most likely we're going to be expressing probability as either a fraction or a decimal. Now, before we get into the concept of geometric probability, probably better take a second and just go back and talk about some simple probability that you guys learned back in the day. So this is probably not going to be anything tough for you here. But our experiment now, everybody, is that we are going to roll one standard six-sided die. And remember, guys, a single die right here is the singular of what we more commonly refer to as dice. But dice is plural, and when you have only one of them, it's called a die. So let's get started right here. First of all, the probability of rolling a 5. We need to understand how to read that notation right there. The probability of rolling a 5. Okay, so the formula we wrote down on the last slide was that probability is always found by taking the number of possible successful outcomes on top divided by the total number of outcomes on the bottom. So let's think about what happens when we roll a six-sided die. Well, because it has 6 sides and there's 6 different results that can happen, I usually like to do the numerator first and say, okay, there's 6 different things that can happen when you roll a die. And if we are defining a successful outcome as being a 5, the question now is how many out of those 6 possible outcomes are a 5? And the answer is there's only one face on that cube right there that'll give you a 5. So the probability of rolling a 5 is going to be 1/6. We said probability was normally going to be, in fact, always going to be between 0 and 1. And sure enough, this likelihood of 1/6 is in that range right there. So not a real good probability that you're going to roll a 5. If somebody came up to you and said, hey, I'll bet you $20 right here that you can't roll a 5, you probably should not take that bet because you're actually 5 times more likely to lose that bet than you are to win. Okay, but let's move on right here to something a little bit more interesting. Probability of rolling an even number. So again, you toss that die, and there are 6 possible outcomes. But now the concept of success has been redefined now. It's not just rolling a 5, but now our favorable outcome would be rolling any even number. So ask yourself, out of those 6 possible outcomes, how many of them are even? Well, there's a 2, there's a 4, and there's a 6. So 3 of the possible 6 outcomes there are even. So our probability of success of rolling an even is 3 out of 6. And one thing you guys never need your math teacher to tell you from here on out, anytime you can simplify a fraction, you should do so. So our probability of rolling an even number is 1/2. If somebody came up and wanted to make that bet with you, it's a toss-up right there whether you should take it or not. You're just as likely to win that bet as you are to lose it. Now, how about this one right here? Probability of rolling a number less than a 5. So again, we toss a 6-sided die, and there's 6 possible outcomes here. And when we think about success now, we want to know how many of those 6 are going to be less than 5. So our successful outcomes would be the numbers 1, 2, 3, and 4, not 5 and not 6. So there's 4 successful outcomes that could happen, and we simplify the 4 over 6 to get a probability of 2/3. If someone came to you wanting to make that bet, according to the laws of probability there, that is a bet that you should take, because since 2/3 is more than a half, that means you're more likely to win that bet than you are to lose it. All right, and let's look at these last 2 right here. This one right here, the probability of rolling a number less than 10. Remember, guys, this isn't Monopoly. We're not throwing 2 dice. We're only throwing 1 die. So when we toss it, once again, there's 6 possible outcomes that could occur. And when you ask yourself now, how many of them would be successful? How many of them would be less than 10? The answer, which may be obvious to some of you already, is all of them. There's only 6 things that can happen when you toss a die, 1, 2, 3, 4, 5, or 6, all of which are less than 10. So there are 6 successful outcomes out of a total of 6 possible outcomes. And anytime we're dividing a number by itself, this is one of the few cases here, guys, where probability is actually going to equal 1. That means that this event is guaranteed. We know for a fact that every time we toss a 6-sided die, we are going to get a number that's less than 10. And the last one I got for you right here, what was the probability of rolling a number greater than 10? Well, just like always, 6 possible outcomes could occur, but out of those 6, how many of them are actually greater than 10? The answer to that is none of them. It's impossible to roll a number bigger than 10 with just 1 die, and 0 divided by any number other than 0 is going to get you a probability of 0. So these last 2 right here, guys, were really meant just to show you the odd cases right there, where you can end up with a probability of 1, meaning an event is guaranteed, or 0, meaning an event is impossible. But in every other case, and as I said, the vast majority of them, you're going to get a probability that's somewhere greater than 0, but less than 1. And that's what happened in all of these cases right over here. We ended up with probabilities between 0 and 1. Okay, so now that we have a kind of a rudimentary understanding here, or maybe a reminder of what basic probability looks like, let's talk a little bit more specifically now about the concept of geometric probability. How does probability relate to geometry? Well, there's actually 2 different ways of defining probability here with geometry. One of them, you'll notice, involves length, and the other one right here involves area, but both of them are probabilities. And in both cases, you're taking the measurement of the desired region, meaning the spot where you actually want to be, divided by the total, meaning the measurement of everything out there that you could possibly end up at. And that's the same whether we're talking about length here on top or area here on bottom. That formula can feel a little weird, but once we dive into it, most people think these things are relatively simple to understand. So let's take a look at what's going on right here. A point is going to be chosen at random on line segment AD. Now, AD obviously begins right here at A and ends over here at D, and we want to know the probability that the point that we choose at random now lies on the given line segment. So let's see what's going on here. The first thing in part A, we want to know the probability that if a point is chosen at random on AD, which is the entire line segment there, we want to know the probability that that point ends up on line segment AB. Okay, well, since we're talking about line segments right here, this is the variation of the formula that we're going to be using. Desired length divided by total length. And once again, I like to think about the denominator first. All right, if we think about the total length, this line segment begins at A, which has a coordinate of -8, and it ends right here at D, which has a coordinate of 4. So you're going to ask yourself, what is the total length of this line segment everywhere that this point could be chosen? And from -8 to 4, that's going to be a total length of 12. The way we got that, if it's not obvious, guys, you're always going to take your right endpoint, which in this case is 4, and then subtract the left endpoint from that. That subtraction always gives you the length right there. So this is a 4 minus a -8, and the minus -8 becomes a +8, and that's how we end up with 12 then for the denominator. Now, for the numerator of this probability, we want the desired region right here, the desired length. We want this point to fall on line segment AB. So now we just need to know how long that is. And from -8 to -3, again, you can take this right endpoint, -3, minus the left endpoint, and that's going to get you 5 right there. That fraction does not simplify, so that's our answer for part A. The probability of a point chosen on AD also landing on AB is 5/12, or a little bit less than 1/2. And sure enough, that probability is in between the magic numbers of 0 and 1. Okay, let's talk about B now, the probability of a point landing on BD. So the denominator again is the total length of this line segment, and lucky for us, that's not going to change. That's still 12 like it was in the last case. But now the distance from B to D, we would take 4 here on the right and subtract -3 from that and get 7/12. So that probability is better than the probability of hitting AB here in part A. We're more likely to land on BD than we were over here on AB. Okay, how about C? The probability of landing on line segment CD. All right, so once again, we're going to put the same total denominator down there. All of AD has a length of 12, and the distance from C to D, from 2 to 4, is only 2. And again, anytime we can, we need to simplify our probabilities right here, so we end up with 1/6 for that probability there of landing on CD. So that's the lowest probability by far of the 3 that we've talked about. And the last one I wanted to discuss right here uses the magic word here in probability, that word being or. So that or right there is important right there. When we want to know a probability of a point landing on either AB, right over here, or CD, ask yourself, are we increasing or decreasing the probability right here, the likelihood that we would hit it, if there's 2 possible regions we could land that would be deemed successful? And the answer to that is that we're going to increase our probability. So once again, the denominator does not change. That's still going to be 12 down there on the bottom. But for the probability of AB or CD, we know that the length of AB, we did that work already, was going to be 5. And when you see the magic word or in probability, that always means we're going to add to it. The length of CD was 2. So we have 2 possible successful regions right here. We'd have to add those probabilities together and get a 7/12 now for the probability of hitting either line segment AB or line segment CD. All right, so that's kind of your first little foray into geometric probability, and that deals with length. That's kind of the easy warm-up right there. The much more interesting thing for us, and the reason we're talking about this within Chapter 10 right now, is because we can do probabilities with areas as well, and that gets a little bit more interesting. So let's take a look at 3 examples, I believe, that we have right here. And this first one is actually a pretty easy example, but boy, does it freak people out. They look at this and they say, wait a minute, Fontana, you screwed up. You didn't give us any dimensions or any measurements. We don't know how long anything is. Well, that's kind of the interesting thing about this problem. Let's read it. If a point is chosen at random inside the rectangle, so I'm going to highlight the rectangle here in green. So we know, if you think about throwing darts, everybody, you know that your dart is going to hit that rectangle somewhere. Okay? We want to know the probability that that point is also going to land inside the triangle. Okay, so there we want to know what's the probability that we're going to hit inside the yellow triangle here if we know that we're somewhere within that green rectangle. Okay, and again, this irritates people a little bit because there were no dimensions given. Well, one problem-solving strategy you guys might want to keep in mind as you move forward right here, and if we take any standardized tests ever again or anything like that, you might want to think about the concept that a lot of times when they don't give you information that you thought would have been relevant to solving the problem, that's actually a hint that you were wrong, and that information is not necessary. Now, when we think about the formulas here for area of a rectangle and area of a triangle, both of them involve base and height. So I don't know how long this line segment is down here on the bottom, but that red segment that I drew is the base of both the rectangle and the triangle. So I'm going to generically call that B. Now, what I really hate to tell you is you could make up any number that you wanted right there for B, and this would work out just fine. The other thing we need for the area of both a rectangle and a triangle is the height. And so if I were to draw the altitude coming from this point right here, straight down, and remember guys, altitude means perpendicular, all right, that red segment that I just drew is the height of both the triangle, but of course it's also the height of the rectangle as well. So let's talk about what's going on right here. There's actually two different shapes that we have to work on here, guys. We've got the area of the rectangle, and then we also have to worry about the area of the triangle. Let's find both of those. Well, the area of a rectangle, this is going to be funny, guys, because I'm really going to combine steps 1, 2, and 3 all into one. The formula for area of a rectangle is base times height. Now, that's what I would normally tell you to do for step 1, write the formula. Step 2, fill in what you know. So what is the base of this rectangle? Well, we generically called it B. And then what is the height of this rectangle? Well, we generically called that h. So if we were going to do a step 2, I'd just be putting a b in for b and an h in for h, and we wouldn't really be accomplishing anything. And then step 3 would be to simplify. Well, you can't simplify b times h because those are two variable quantities and we don't know anything about them. So guys, this is as good as it's going to get. That's the area of your rectangle, bh, whatever those numbers are. Now, the area of a triangle is almost the same formula, but it starts with a 1/2. So it's 1/2 times the triangle's base times the triangle's height. Well, once again, the base of that triangle, we don't know anything about it other than the fact that it's B, and the height of that triangle, we don't know anything about it other than the fact that it's H. So this, again, there's nothing to substitute, there's nothing to simplify, and that's the formula right there, 1/2 BH for area of the triangle. So now, if we wanted to think about the geometric probability of hitting the triangle right here, well, the formula we were using, actually a variation on that, we're now going to be talking about this one right over here. That geometric probability is desired area divided by total area. So as we look at this, the region that we're trying to hit is the triangle. So I maybe just put this up here, area of the triangle. And the total region that we could hit is the area of the rectangle. Okay, so that is as good as this formula is going to get, and now let's fill in what we know. The area of the triangle we came up with a moment ago was just 1/2 times b times h, and you can't do anything else other than that. The area of the rectangle underneath it, oh boy, is going to be, there we go, right there, simply b times h, and there's nothing else that we can do with that. The only question remaining is whether or not this expression can be simplified or not. And one thing you guys saw in Algebra 1, and you're going to see a lot more in Algebra 2, is when you have identical factors on the top and the bottom. Remember, factors are numbers that are being multiplied by other numbers. Those identical factors will cancel each other out. So that b cancels with that b. That h cancels with that h, and the only thing that remains here in this expression is a 1/2 up on top. So, and technically that gets divided by a 1 that was on the bottom. Well, 1/2 divided by 1 is simply 1/2. And guys, that is the answer to this question. What we're saying here is that the yellow triangle makes up exactly 1/2 of the area of the overall green rectangle. And I think if you look at that, you can understand that that's right. If you broke it up just maybe into like this rectangle right here, I think we can see that the shaded and unshaded regions are the same. And another rectangle over here, again, the yellow shaded and the white unshaded are going to be exactly the same as well. So it really didn't matter what the values of B and H were. A probability problem like this is always going to give us 1/2. We're just as likely to hit the yellow region as we are to hit the white region. Now remember, guys, we're talking about this concept right here of at random. I mentioned throwing darts before. Darts aren't quite random because there is skill involved. If you were trying to hit the yellow region and you knew what you were doing, you'd probably have a probability better than 1/2 of hitting your target. But we're just talking about randomly throwing without really looking at it at all and trying to figure it out from there. Okay, two more problems that are probably a little bit more typical, like the ones that we are going to see. And in this one, we have a square with a side length of 10 inches and a circle inscribed within that square. And we want to know the probability of hitting the shaded region. So to do this, everybody, there's a couple of things that we need to find before we get started. We're going to begin with area of the square. Okay, since we have a square right here, we know that the base and the height are both going to be the same. So I know that this side over here is 10 inches. And 10 times 10 is going to give us 100 square inches for the area of that square. Second thing we better find is the area of the circle. And the formula for area of a circle, hopefully we recall, is pi times your radius squared. So we need to know what r is. So pi times, well, our radius is going to be a line segment that goes from the center of that circle to any point located on the circle. And you want to be smart about where you draw this, because if I drew this segment right here, technically, yes, that is a radius, but that doesn't help me at all figure out how long that radius is. The smartest radius to draw would be one that goes right over here. And if we think about this, we know that the entire top side of this square has a length of 10 inches. That, if we copied it down, would be the diameter of that circle. The radius is going to be half of that, though, so 5 inches is going to be the radius of our circle. So our radius of 5 inches is now going to get squared. And there's not a whole lot we can do to clean this up, guys. The 5 squared is going to be a 25. We like to keep our answer exact, so just stick the pi there, and the inches got squared to make 25 pi square inches. Now, as a real quick comparison right here, if we think about these two areas that we just came up with, 100 is a nice, easy number for us to latch onto. We understand it. 25 pi is irrational, but we might just want to think quickly about the concept that pi is just a little bit more than 3. 25 times 3, excuse me, 25 times 3 is 75. So the area of the circle we're saying here is a little bit more than 75, probably in the neighborhood of about 80 square inches. And if you think about how that compares to the 100, I think that seems realistic. Okay, one of the things that we're going to start doing though now, guys, is doing this right here, trying to find the area of a shaded region. And the shaded region is what we colored here in green. And some of you are going to find this really, really easy. The rest of us need to work on it a little bit. What we need to do for area of a shaded region right here is basically take the outer area here, the shell of the region that we're dealing with, and then subtract from that the inner portion, which is not shaded. So in this case right here, the outer area, we were dealing with the square right there, is 100 square inches. In fact, I'll go ahead and include units for now. And the inner region, the part we didn't want right there, was the circle, which was a 25 pi square inch measurement here. So as we try to simplify this, there's actually not really anything that you can do here because 25 pi has this factor of pi at the end and the 100 does not. So that actually can't be simplified at all, and we're just going to leave it as 100 minus 25 pi. The one point I did want to make here is to talk about units. When you've got square inches and you're subtracting or adding those quantities with the same unit, the units just tag along right here. So that's 100 minus 25 pi square inches, and technically there's parentheses around that. So that weird number that we just have right there is the area of the green shaded region. And so the last thing that we have to do now here, guys, is go ahead and find the probability of hitting that shaded region. So let's write it out this way. So the probability of hitting the shaded region right here would be your desired area divided by your total area. Well, the desired area is what we just came up with right here. We were hoping to hit the green shaded region, and so that right there is an area of 100 minus 25 pi. That's the region we were hoping to hit. And again, that's going to be in square inches right there. Down on the bottom is the total area that we could potentially hit. And we knew that we were landing in the square here, so that's going to be 100 square inches down there on the bottom. Now, you guys are going to get a lot of practice at this next year in Algebra 2. What you cannot do in this case is cross out those 100s. It's really tempting. And in fact, some of you are probably saying, wait a minute, Fontana, you did that exact same thing right here. Well, no. Those B's and H's that we crossed out in example 5A were factors, things that were being multiplied by other numbers within that expression. But in this case right here, that 100 up on the top is being subtracted with the 25 pi. That makes it a term, not a factor. The other thing that should make you realize that that can't be done, if the 100s did cancel out, this is your answer right here. Well, the answer to a probability problem can't be negative because we said that the lowest possible probability you could ever end up with would be 0. So that wouldn't make any sense there at all. Okay, I don't know if this is good news or bad news, guys, but what that means is that we actually can't do anything else right here to simplify this expression. So technically, I guess we could factor out a 25, but what we're going to be doing in most of our cases right here is going to our calculator and trying to express this answer right here, guys, as a decimal in most cases. So bear with me for just a second right here, guys. I'm going to go to a calculator right here, and I don't actually have an app for the calculator that you guys are using, but let me go ahead and we'll try the Desmos Scientific calculator here. This isn't a bad one if you guys want to download this, and whoa, let's see what we can do here, everybody. I'm going to make this a little bit easier to see. And here we go. We want to do a fraction, and up in the numerator, our area of our shaded region was going to be a 100 and then a minus 25 pi. Got it. Down on the bottom, our denominator was just going to be 100, and then when I go ahead and hit enter, there's our answer right there as a decimal of 0.2146. And I don't quite know why, but most textbooks, including yours, I believe, are going to ask you to come up with these probability decimals to 4 decimal places. So we're going to go with a 0.2146. All right, and that 0.2146, that's going to be our answer there, guys, our probability of hitting the shaded region. Now, one other thing we could do, both of these are fine, but they're not necessary, would be to try to express this probability as a percentage. And what I hope you guys remember from middle school math is that if we want to take a decimal and make a percentage out of it, we simply, you don't need to write this down, just multiply that by 100. And to do that, you just take your decimal and slide it 2 places over to the right. So you could also write this number as 21.46%. You just need to make sure that you include the percentage sign at the end of all that. So I would be perfectly fine with either one of those 2 answers right there. Both of them are equally correct. And as we think about whether or not it's realistic, let's go back to the diagram right here. Ask yourself, does it look like 21% of that square is shaded there in green? Hopefully you'd see that the answer to that is yes, and we find that easy to swallow. All right, so that was a pretty good problem here. One more and then we're done here, guys. Let's take a look at what's going on right here. We have what are called two concentric circles, meaning two circles with the same center here. The inner circle, this smaller one, has a radius of 3 centimeters, and then kind of the width of that donut right there between the two circles ends up being another 3. Okay, so we've got to do a couple of areas right here. We've got to do the area of the big circle. We've got to do the area of the small circle. And then finally, we're going to have to do the shaded area as well. Okay, so area of the, actually I'm going to start with the area of the small circle first. That's going to be pi times your radius squared, and the radius of the small circle, we looked at that just a second ago, is 3. 3 squared is going to be 9 right there, so 9 pi is going to be the area of that small circle. Okay, let's take a look at the big circle right here. That one is also going to be pi times your radius squared. But as we think about, let me switch colors on you here. As we think about the radius of the big circle, I'm going to draw just one radius going right down here. There we go. We know that this inner piece is 3. This outer piece is 3 as well. So when we put those two together, we end up with a radius of 6. For the big circle right there. Squaring that 6 is going to get us 36, so 36 pi is going to be the area of the large circle. Okay, for the shaded region, we're always going to take the outer area minus the inner area. So the big circle's area, we said, was 36 pi. We're going to subtract from that the area of the small circle on the inside, which is going to be 9 pi. And again, just like an x, these are like terms here because they both contain the same factor. So we simply subtract their coefficients. 36 pi minus 9 pi is going to be 27 pi for the area of that shaded region. And the last thing we do now is try to find probability here of landing in the shaded region. So what we're always going to do here for geometric probability in a case like this is go back to this formula right here, desired area divided by total area. Okay, so we are hoping to hit the shaded region in this problem, and our shaded area is 27 pi. The total area we could hit is given to us by the area of the big outer circle, which is 36 pi. Now, what I would really like you guys to get in the habit of doing is not even going to the calculator right here, but recognizing that the pi's are identical factors on the top and the bottom, and they're going to cancel out. If you are going to do this in your calculator, you have to remember to use the fraction button or to do parentheses. But if you type this into your calculator, 27 pi divided by 36 pi, you are not going to get the right answer. You need parentheses around the 36 pi, or better yet, just type it in using the fraction button as it appears right here, or better yet, just be aware that the pi's cancel and don't even put them into your calculator. 27 and 36 are both divisible by 9, and then we end up with an answer right there of 3/4 for the probability of landing in the green shaded region. And so ask yourself that question, does it look like 75% of that circle is shaded in green? A lot of times with circles people say no, but that's the way that one actually works out. Okay, guys, that's all of 10.8. Let's give that homework assignment a try and see how we do. Make sure you comment and ask questions, and I'll get videos posted for you guys as soon as I can.